Okay, good. So, first of all, thank you for inviting me to the University of Tokyo. I suppose joined with Okinawa Institute of Technology. The talk has a website, and it's defined to be omega epsilon beta, and it's HTTP : whatever is written over there. And the handout, there is a copy of the handout there, and eventually there will be a video there. And oh, I apologize for speaking with a mask. I just recovered from COVID, and the recommendations are to stay with a mask for a while, so I'm staying with a mask for a while. And so I should also say that I've given a good number of talks in Japan already. I've been here for a little while, and I didn't want to repeat any of them. So this is kind of a fresh talk on a subject which isn't my main interest. My main interest is to find strong and fast and homomorphic knot and tangle invariants, and I've explained it in other talks that I've given on web/Nara, web/Kyoto, and web/Tokyo. You can find the website for these talks, and here are the front pages of each one. And so today is kind of a little bit of an aside for me. I should also say that to some extent I've looked into my own psychology, and why did I put this slide here? Partially to be apologetic, partially to say, I'm going to tell you things that are so simple, and it's a bit embarrassing, right? So I want to show you that I'm also doing complicated things, okay? But then I had second thoughts, and it's exactly the opposite. If you can say something simple that's new, it's a lot better than if you can say something complicated that's new. And in fact, this is a general property of mathematics. So addition and subtraction are much more valuable to the world than category theory. So if you can say something new that uses only addition and subtraction, then you're way better than if you have to use high-level, fancy, complicated stuff. I haven't gotten to the level where I can say new things that use only addition and subtraction, but I shouldn't be apologetic about being very low level, very simple-minded. Anyway, my talk follows a handout. I think you have a copy. It's partially supported by the NSERC and by the Chu Family Foundation. I have to acknowledge this. And it's joint work with Itai Bar-Natan, Eva Halachiva, Nancy Sheriff. I forgot to put their pictures, I'm sorry. And basically I will tell you that finite type invariants, so there is something called finite type invariants. We already heard about them. So they have a type. So an invariant of type D, say D is equal to 8, you can ask yourself, how long does it take to compute an invariant of type 8 on a knot with n crossing, where n is large, 1,000, okay? And I always thought, and I think everybody who ever thought about it, thought that the time was n to the d, so 1,000 to the 8. And we recently discovered that the time is roughly the square root of that, so n to the d over 2. Not quite, and I'll tell you exactly what it is in a moment, but it's way better. So you can compute relatively high degree invariants, degree 8 say, at relatively reasonable time. Okay? So that's the content of my talk. First few conventions. So n underscore means the set of integers from 1 to n. That's easy enough. And 2, so when I estimate the complexity of computing something, I care about polynomials and I don't care about logarithms. So for the purpose of these computational estimates, I will define a relationship tilde. Tilde is somehow equivalence of growth rates. And I will say that n cubed grows the same as 2023 times d factorial times log n to the d times n cubed, right? Because this is just a logarithmic term. D factorial is just a constant. I really don't care about it. 2023 is obviously a constant, and the next year it will be 2024, so it's sort of a constant. And n cubed is the same as that n cubed. Okay? Questions, comments? No. So here is the key preliminary, the main point, and it has nothing to do with knot theory. So suppose you have Q, a subset of n underscore, so the raised to the power L. So basically the integer lattice in L-dimensional space, but the n by n by n box in it. So here is the two-dimensional example. So Q is the dots, and it's a subset of the box of size n by n. And let lowercase q be the number of elements of a set Q. And I'm assuming that it's much bigger than 1 and much smaller than the full set. So it looks roughly like this, some dust in the box. Okay? And tomorrow, somebody, your professor, your boss, I don't know, is going to tell you, here is a rectangle, R, inside the cube, the big cube. How many elements of Q are inside this rectangle? And your boss will expect the answer immediately, meaning in time proportional to 1. Okay? So what can you do today so as to be ready to give the answer quickly tomorrow? Okay? And the claim is that in time roughly proportional to Q, so in time roughly proportional to the number of points, which is again a lot less than the overall size. So in time roughly proportional to Q, you can set up a table so that tomorrow you will be able to give the answer in time 1, roughly proportional to 1. Okay? So just so that you understand the significance, just so that you understand that it's not easy, let's fail in 2 different ways. So failure number 1 is, let's not prepare anything, okay, today. And simply tomorrow, when we're given R, we'll count. So when we will be given the rectangle, the red rectangle, we will start counting 1, 2, 3, 4, 5, 6. Gee, it's more than I can count. Okay? That fails because you may count up to a significant fraction of Q. And Q, although much smaller than the total number, is much bigger than 1. So you have to count, it will take you too long to count. And option number 1, failure number 2 is, so let's make in advance a lookup table which says for every rectangle how many elements are in it. Just let's make a table of all the rectangles, and for each one say how many there are. The problem with that is that there are too many rectangles. The number of rectangles is proportional to n to the power 2l. Basically, you have to choose two numbers in each coordinate. So the number of rectangles is n to the power 2l. And if you wanted to make a table of all of them, it will take you at least time n to the 2l, which is, well, more than what I've allowed you to do. Okay, which is more than what you have between now and tomorrow. Okay, so that doesn't work. So let's unfail now. Here's how you do it. Okay, so you make a restricted lookup table. Oh my God, last time I gave a talk in this room, I was wise and brought an umbrella from outside to use as a pointer, but now I have to use a laser pointer, which I like less. So, so make a lookup table, a restricted lookup table. So a lookup table that only for dyadic R gives you the number of elements in this R, but only if this number is greater than 0. So what's a dyadic R? So basically I put a scale on the outside, and if you look at the left bar, it goes black until the middle and then white. If you look at the next bar, it's cut in half, so you have black to the middle and then white and then black again and then black, sorry, and then black again and then white. If you look at the next level, so basically, and you see such things on rulers, it's not an unusual sight to see. But said differently, you look at the whole interval from 1 to n, or you cut it in half and look at the 2 halves, or you cut it in 4 and look at the 4 quarters, or you cut it in 8 and you look at the 8 subintervals that you get, or you cut it in 16 and so on. So a dyadic interval is one of those intervals, and a dyadic rectangle, I mean, the picture is 2-dimensional, but it could be L-dimensional. So a dyadic rectangle is a rectangle all of whose coordinates are dyadic. So for example, this purple rectangle is, I think I should have blown it up. So this purple rectangle is dyadic because along the x-coordinate, it's a quarter from here to here, and along the y-coordinate, it's a 1/16, I think. Okay? The number of dyadic intervals is actually pretty big. But I don't care because you'll see. Okay? Because I only use the ones which are non-empty. So how do I make the table? Well, so for every element of the set, so basically for every dot, I look at all the dyadic intervals that contain it and add 1 to all of those entries in the database. So I basically start with an empty lookup table in which no rectangles are marked, and for each point x, I look at all the dyadic intervals that contain, all the dyadic rectangles that contain it, and for each one, if it's already in the table, I increment by 1 the number of points in it, and if it's not in the table, I put it in the table with 1 and with a total of 1 inside it. Okay? So clearly when I will be done, I will get a table of all the dyadic of all the non-empty dyadic intervals, and for each one exactly how many points of Q are in it. And how long did it take to make this table? Well, for each point, the number of dyadic intervals the number of dyadic rectangles containing it is logarithmic. Basically, it's at most the log, so in each coordinate you have at most log of n dyadic intervals containing a point, and you have L coordinates, so the total number of rectangles containing each point is at most log 2 of n to the power L. But I had to go to do it for all points, and there are q points, so the total is q operation, just as I promised. Okay? Now, entries for empty dyadic intervals are not needed and not created. So this is what I do today. And then tomorrow, when I will be given a red rectangle, and I will be asked to tell you how many points are in it, and answer quickly, I will decompose it into a union of dyadic rectangles, look up in the table how many points are in each one, add the results, and this the time that it takes me to give the answer will be as long as there are purple as long as there are dyadic rectangles inside the red one, inside the big one. But you can count this, and basically you can look at the binary expansion of the endpoints of the red rectangle and see that the number of dyadic rectangles in it is bounded by 2 log 2 of n to the power L, which is roughly 1. It's logarithmic. So, so this is it, we're done. Are you okay? This is the key point. Okay, so you can count, well, in this situation you can count quickly, more quickly. Okay. I actually need a slight generalization of that. So, without changing the conclusion, just replace, instead of counting how many points there are, suppose you have a function defined on the rectangle, but it's a function with kind of a union of delta function support. So it's a function, it's a sum of delta functions. So it's a function which is supported on some set Q, which is small, okay? And it takes values in some vector space whose dimension is small, is roughly 1. Then you can sum this function quickly in exactly the same way. Why? Basically, instead of tabulating the number of points, you tabulate the sum of the values, okay? And inside each dyadic rectangle. And the fact that it's a sum in a vector space doesn't matter, because the vector space is of small dimension. So you just have to add a relatively small number of coordinates, and that doesn't add to and that doesn't change the total time estimates. Okay? Good. Okay, so this is the preliminary, and now we can start with content. So, first of all, a word about Gauss diagrams. So, there is a standard way of representing knots as so-called Gauss diagrams. So, basically, you walk along the knot and record each time that you go through a crossing. So, first of all, I open the knot so that it's a long knot. And then I went through a crossing, let's call it point number 1. I walked through a crossing again, let's call it point number 2. Then 3, then 4, then 5, then 6, then 7, then 8. So I make a long interval, really the parameter space of the knot, and I mark on it points 1, 2, 3, up to 8. And then I put an arrow from each, corresponding to each crossing. So each crossing has an upper strand, which is now an integer, and the lower strand, which is another integer. So I put an arrow going from the upper strand to the lower strand. So this crossing will correspond to an arrow from 1 to 4, and indeed there is an arrow here from 1 to 4. Now, crossings also have signs, and I'll just mark the sign next to each arrow. So a Gauss diagram is a collection of sign arrows. So this is for a 4 crossing knot. And if we had a 100 crossing knot, the Gauss diagram might look something like this, except here I suppressed the signs to make it less cluttered, but think that each arrow also has a sign. Okay? And now some definitions. So calligraphic G will be the set of the vector space of linear combinations of Gauss diagrams. And calligraphic G sub D, or, sorry, this is not the quotient symbol, this is or. Okay? Or calligraphic D sub less than or equal to D will mean the subset of G, the subspace of G, with either exactly or at most D arrows. Then there is a function, a linear map, phi sub D, going from G to GD, and it's the map which maps every Gauss diagram of size D, sorry, every Gauss diagram of any size to the sum of all subdiagrams of it. This should be D, I'm sorry. To the sum of all subdiagrams D of G, which have exactly D chords in them. So for example, if our G is the Gauss diagram shown here in the background, then phi 3 of it will be the sum of all the subdiagrams of size 3 as shown here. A lovelier notation, instead of writing D inside G and the size of D is D, is to say, so use the binomial coefficients. So, right, n choose k is the number of k element subsets of n. So if you use a set at the top instead of n, then set choose k means the number of k element subsets of the original set. And so if I use an arrow, the Gauss diagram at the top, then G choose D means the set of all D element subdiagrams of G. So I'm summing over G choose D, I'm summing over uppercase D inside G sub D, G choose D, I'm summing D itself. Okay, so phi sub D is just the sum of all D arrow subdiagrams. And then I will define phi sub less than or equal to D to be the sum over all E of phi sub E, where E is less than D. So it's the subdiagrams of size less than or equal to D. So 2 comments. First of all, I'm sorry, I'm ventilating and it's a bit because of the mask. So first of all, how long does it take to compute phi sub D? So if you're naive, you basically have to look at all D arrow subdiagrams. Basically, you have to look at all those Ds, and their number is the size of G, choose D, so n choose D, and that's roughly n to the power D. So that's quite a long time. So that's one comment. And the second comment for use later, let me introduce some notation. So if you already have a subdiagram D of the big diagram G, then it has endpoints, and I will label the endpoints D1, D2, D3, D4, D5, D6, going from left to right. So each of these Di is a number between 0, or maybe 1, and 2n. Okay? And just for completeness, I will make the leftmost label, I'll add an extra leftmost label, D sub 0. So it's the constant 0. And I'll add a rightmost label, D sub 2D plus 1, in our case 7. And it's 2n plus 1, so it's the rightmost index. And finally, I will also refer to the gaps between the legs of D by their numbers. So this is gap number 1 is from here to here, from D0 to D1. Gap number 2 is from D1 to D2, and so on. Okay, this is for use later. Okay, next. So how is this related to finite type invariance? And in fact, this is the only thing you need to know about finite type invariant. A knot invariant is finite type of type D if and only if it is of the form omega composed with phi less than equal to D, for some omega which is a linear functional on the space of Gauss diagrams with less than or equal to D arrows. So the standard definition is a bit different, and the equivalence between this definition and the standard definition is a theorem of Gusarov, Polyak, and Virol. And one direction is easy, the other direction is the hard side, and in fact, in my opinion, it's not even sufficiently well understood. So I've gone through the proof several times, my student went through the proof several times, it seems to be right, but somehow I can't remember it. And the fact that I can't remember it suggests that I don't understand, there is something conceptual there that I'm missing, and I'm still missing it. It's still not conceptually clear to me, but it's nevertheless true. Okay? Okay. Now, if this makes you think that finite type invariants are easy, then they're not, because but the difficulty is in omega somehow. So not every omega gives you an invariant, or said differently, phi is not an invariant. It's only if you're very careful about the choice of omega that you get an invariant. Okay? And maybe just a word for advertisement. So the theory of finite type invariants is very, very rich. I will not go through it now, but there are many, many knot invariants that are finite type or that factor through finite type invariants. And in fact, it's possible that finite type invariants separate knots. So people care about them. Anyway, so all we need is a fast algorithm to compute phi less than or equal to D. Because if we had one, we would compose it with omega once omega is given and be done. Okay? Now, so far computing phi sub D takes roughly time n choose D, which is n to the power D, and I'm claiming that we can square root that. Okay? So here's the precise statement. So on an n-arrow Gauss diagram, phi sub d, well, here I wrote phi sub less than or equal to d, but if you can compute phi sub d, then go ahead and compute phi sub d minus 1, phi sub d minus 2, using the same algorithm, and then add them, and that's a total of d factors, d summands, and a factor of d is like 1 from our perspective. D is a constant. So I claim that on an n-arrow Gauss diagram, you can compute phi sub d in time which is roughly n to the ceiling of d over 2. So if d is equal to 8, then d over 2 is 4, the ceiling of 4 is 4. If d is equal to 7, d over 2 is 3.5, the ceiling is 4, so it's n to the 4. So you can nearly get to 1/2 to square root, but depending on the parity. Okay? Are you with me? Are you okay? Okay. So the strategy is very simple. So what I will do, I will, instead of placing D, instead of choosing a subdiagram of size D, I will divide the task into two parts. I will place a subdiagram of size P, and I will call it uppercase P. And then I will look up, so I will create a table in advance that will allow me to look up in how many ways I can place a subdiagram of size L between the legs of the diagram of size P, and then I will do it for P and L such that D is equal to P over L, and that's how I will count the diagram D, how many ways I can place a diagram D. But before that, so if you have two subdiagrams, P and L, you can simply reconstruct their union. I mean, you need a little bit more information. You need to know the legs of L. So for each leg of L, you need to know in between each, so in between which two legs of P you have to place it. Again, if I know L and P, how do I merge them? So in order to be able to merge them, I need a non-decreasing placement function which goes from the interval from 1 to 2L, so basically from the legs of L to the numbers between 1 and 2p plus 1, so to the intervals between the legs of P. And once I have such a placement function and a diagram P and a diagram L, it makes sense to look at B merged with L using the placement function lambda. I'll call it B sharp lambda of L, and call it D. And now, the set of all, or phi sub D of G, which was defined before to be the sum over all subdiagram of size D of G of D, is equal to, so forget this combinatorial factor for a moment. You first place a subdiagram of size P, and lowercase p, and call it uppercase P. Then you sum over all placement functions. By the way, how many placement functions are there? Well, I don't care. I mean, this is a number less than D. This is a number less than D. Or so it's some combinatorial function evaluated on numbers less than d. So it's a constant. So it's 1. So this summation is a summation over a set of size 1. Okay, or size equivalent to 1. So again, it's a summation over p of a summation over the placement functions of a summation over subdiagrams of size L which obey displacement function, meaning such that L sub I is in the corresponding interval between the legs of P. So it's in the interval between P of lambda I minus 1 and P of lambda I. And then for each such P and L, you just take P sharp lambda of L, and that reproduces D. Now that was an overcounting because we counted D's which are split into two colors, the P color and the L color. But the number of splitting into two colors is D choose P. So if I divide by D choose P, I get the right answer. Are you okay? Maybe not. Okay, I'm doing my best, I'm sorry. Anyway, I claim that this inner summation is really a lookup situation. So define a function theta sub g from sequences of length 2L of integers between 1 and 2n, so the whole length of the Gauss diagram, into Gauss diagrams of size L, sorry, not 2L, this should be L, by mapping every sequence of integers to, well, if this sequence of integers, if these integers are the ends of some Gauss diagram, you map it to that Gauss diagram. If not, you map them to 0. And then phi sub d, or maybe the innermost part, simply becomes the sum of the values of this function on a rectangle. The rectangle defined by the legs of the outer core diagram, of the outer arrow diagram, the diagram P. And this takes time 1 to compute if you prepare a lookup table in advance, as in the preliminary. So how long did it take us in overall to compute phi sub d? So we still have this summation here, which takes time n choose p. This is 1, so we don't care. And then this took time 1, but we had to prepare for it by making the lookup table. The lookup table has size comparable to the number of subdiagram of size L. And that number is n to the L. So the total time is n to the L to prepare the lookup table, and then add n to the p for the actual computation. Now, if you take p to be roughly a half of d, then you get n to the d over 2 plus n to the d over 2, which is roughly n to the d over 2, which is what I asserted, QED. Okay? Maybe one more comment. Do I have time for one more comment? Mm-hmm. Okay. So a kind of a funny story. How did we come up with it? So we came up with it, in a sense, this is a negative result. I mean, it's a result that spoiled our mood instead of making us happy. Because we had a fun story to tell, and this ruined the fun story. So, so here's the story. So first of all, let me tell you that planar projections for computations, planar projections of knots are better than braids. So here is a braid. A braid is, I think you all know what it is. I took this picture of a plant with a braided, sort of braided collection of plants. I think this was in Mexico City, but I've seen them in Tokyo as well. Okay? So this is a braid, and this is a planar projection of a knot. And actually, this knot is due to Lisa Pizzarillo, but the planar projection, I've superimposed it on a pancake to emphasize that it's kind of three-dimensional. If you think of it as a topologist, it's embedded, or as a geometer, it's embedded in a pancake shape, so something which is very narrow on one side. So, and braids are even kind of sillier. They have two dimensions or constrained. It's in general true that if knots are given in this way, you can compute better than if they're given that way. Every knot can be given as a closure of a braid, but then if you want to compute an invariant by first writing the knot as a closure of a braid and then computing, it's usually wrong, it's usually hard, because the length of the braid is much greater than the size of the planar projection. If the planar projection has n crossings, the corresponding braid is going to have length L, which is roughly n to the 3 over 2, which is a lot more, and if your computation is exponential time, then computing e to the power n to the 3 over 2 is much harder than computing e to the n. Okay? But then we thought, wouldn't it be even more reasonable, wouldn't it be reasonable to think that if a knot is given as a yarn ball, so what's a yarn ball? A yarn ball is just a ball of strand. Yarn is just, strand. And if you see a knot in nature, you don't expect it to be embedded in a pancake. You expect it to look like a ball of knotted stuff. So wouldn't it be better if we had formulas that could start from a yarn ball rather than a pancake? Wouldn't we be able to get even faster computations? So what exactly do I mean? So let's formalize it a little bit. So you can show that if you have a yarn ball in which the strand is of length L, uppercase L, then the corresponding pancake, so if you squash it to a pancake, the corresponding pancake will have roughly L to the 4 over 3 crossings. So, are there algorithms to compute invariance for a knot given as a yarn ball, which are faster than what you would get by first squishing the knot to the plane and then computing using the planar projection? And so that was the question we were asking ourselves. And you can look it up in this paper. And the only invariant that I know is the linking number. So if this is a two-component link, then computing the linking number when the link is given as a yarn ball link is more efficient than projecting it to the plane and then computing. And we spent a lot of effort, and we were able to show that finite type invariants are also, or we thought were better, or it was better to compute them directly from a three-dimensional representation and not by first squashing it to the plane. We had a clever algorithm that computed finite type invariants faster for yarn balls. And then came the algorithm I just described and made the computation from a planar projection, namely from a Gauss diagram, so much more efficient that we lost the improvement, but the question remains. So it should be that you can do better with yarn balls than with pancakes, because we are in three-dimensional topology, not in combinatorics. But we don't actually know examples where you can do better, except for the linking number. That's it. Sorry, you know, this is way more confused than my usual talks. I would like to attribute it for being sick in the last week and for wearing an oxygen-reducing device during this talk. Okay?
Questions? Can we compute some not invariant using yarn ball? So we consider we have many ways to compute not invariant using pancake or grain. But
yeah.
I don't know.
Well, this is exactly my question.
Uh-huh.
My question is, you know, when you think of knots at least before you've been corrupted by reading too many knot theory textbooks, when you think of knots, they don't look like pancakes, they look like balls. So there ought to be a way to, I mean, if our invariants are genuinely three-dimensional, there ought to be a way to compute their values from a ball. And then it ought to be faster than if you compute them by projecting the ball to the plane and thus increasing the complexity by a great deal. So by the way, you know, if you wanted to store a yarn ball, you would need to store roughly L coordinates, the length, right? But if you want to store a knot, a planar diagram, you need roughly N pieces of information. So this really is a measurement of how big is your thing when you represent it in the computer, okay? And if you try to go from here to here, your presentation grows a lot bigger. So there ought to be a way to avoid it. Again, the only example I know is the linking number. Every other invariant, either I have no three-dimensional formula at all for it, or it's no better than projecting.
I have a question.
Yeah.
Gauss diagram is just for not links.
Oh, there is a version for links. So the version for link, basically, instead of having one parameter line and an arrow indicating the crossings, you would have maybe two parameter lines and arrows indicating the crossings, but the arrows could go either from one line to itself or from the other line to itself or between the lines. So yes, there is a version of Gauss diagrams also for links.
So is the timing similar to?
Yeah, I think everything would be exactly the same. Oh, I take it back. I take it back. I don't think there is a Gusarov-Polyak-Virov theorem for links. So computing phi sub d would be the same. But whether or not it's enough, namely, is it true that every finite type invariant is phi sub d corresponding to some, composed with some omega, I don't know. Because I don't know if there is a GPV theorem for links. And I think this, again, highlights that this GPV theorem is poorly understood.
Can we have some characterization of omega? Such that it's not invariant.
There is some combinatorial characterization of the omegas that give not invariants, and it's not directly easy to use. I mean, there are lots of stories to tell around this, and they're not very short, I'm afraid. Sorry. Oh well, thank you for listening, and I'm happy to answer more questions until the beginning of the next talk.